Hello everyone. In this video, we will be discussing a derivation of Goodman's method. So already in the previous video, we had a discussion on the SN diagram where we got to know that different failure lines, that is the Soderberg line, Goodman line, Gerber curve, and with respect to the yield line, all these points was done. So what was the information or what was the the information which we got related to this yield line is for all ductile materials. In case if you want to protect the material from the fatigue failure means then we need to refer the Soderberg failure line. Similarly, for the brittle material we need to refer the Goodman line, and for the composite material we need to refer the Gerber curve. And this yield line is something which is very common for all the materials which we are not recommending, because till now this yield line is like purely applicable for static load and impact load. Only for the fatigue line we will be discussing this Soderberg, mean Goodman and Zerman curve. In this video, we will be mainly focusing on the Goodman criteria, that is for the ultimate strength or the ultimate stress for the brittle material we will be discussing. Clear? So, first let us have a look on this particular graph. So, we need to understand how to plot this graph. And this graph is basically versus mean stress versus variable stresses. You can able to see this. The mean stress is denoted as sigma m in x-axis, and variable stress is denoted as sigma v, that is plotted in the y-axis. And you can able to see this. We are discussing for the Goodman failure stress line. So let me draw the a Goodman line, that is a failure stress line from A to B, and let me call it as the endurance stress point, and this is nothing but the ultimate stress point. This is the Goodman line. It means if any material which is exactly lying on this particular line means, then we will be calling it as failure due to fatigue for the of the brittle material. Now, since we are talking about for the safest, line to avoid the failure, that is our intention. Let me draw a line which is beyond, not beyond, which is below the failure line. You can able to see. Let me draw a parallel line which I'm drawing parallelly below this AB line. That is a failure stress line. You can able to see. Let me name it as C and D, and let me draw a perpendicular line, and after drawing the CD, I know that this is the factor of safety for the ultimate stress point, and similarly this is the factor of safety for the endurance stress point. This is only for O2D and O2C I'm talking about. Now, after drawing this particular line, let me draw a perpendicular line PQ. Let me consider this PQ is nothing but the variable stress only for this short portion. Why I need to consider the short portion? When we discuss any derivation, always it is recommended to do the derivation for a small panel. So small panel means maybe for one small portions I'll be doing, because the boundary condition is common for the whole part. So if I find out the solution for a small part, a small panel means later I can integrate that particular value to the maximum limit, and the final value can be calculated. So that is how we need to do the derivation. So since for the very smallest part I'll be doing, for that purpose only I have drawn a perpendicular line PQ. After making a PQ line, you can able to see this the PR line. Now this PR will be the mean stress and PQ will be the variable stress. So this is the information we supposed to remember whenever we solve the Goodman's criteria derivation. So theoretically we are writing it as a straight line connecting the endurance limit sigma E and the ultimate strength sigma U, as shown by line AB. Its sketch given below follows the suggestion of Goodman criteria. A Goodman line is used when the design is based on ultimate strength and may be used for ductile or brittle material, but purely it is recommended for brittle material, not for ductile materials. Very rarely they use. Now, from the similar triangle COD and PQD, you can able to see I'm talking about COD and PQD. COD is the bigger triangle, PQD is the smaller triangle which is present in between the COD. So that is why I am calling these two as the similar triangles. You can able to see the angle of O is 90, similarly the angle of Q is 90. Say for example, if the angle of D is somewhere 30 means even for the smaller triangles it is 30. And if the angle of the P, whatever the angle of C is there, the same angle will. That is why we are calling COD and PQD as a similar triangle. If COD and PQD are the similar triangles, means then I can write down by using symmetric triangle equation, that is PQ by CO, which is equal to QD by OD. So PQ by CO, you can able to see PQ by CO, uh, which is equal to QD by OD. That is QD by OD. Here, now what is QD? What is QD? Which is nothing but OD minus QO. You can able to see OD minus OQ divided by OD. And now let me take like the short form of this particular equation. So it is 1 minus OQ by OD. Now we know what is the PQ and what is CO and all this information we know. So let me write, it is PQ is nothing but what? You can able to see here. PQ is nothing but the variable stress. So let me write it as sigma V divided by what is CO? It is induced stress divided by factor of safety, which is the safest limit which is there, which is equal to 1 minus again OQ, which is nothing but mean stress sigma M, and OD is nothing but ultimate stress divided by the factor of safety, that is the factor of safety ultimate stress. Now keeping the variable stress on one side and taking all the things to the other side. So Fe by factor of safety into 1 minus sigma M divided by sigma U by Fs. So which is equal to sigma E again, uh, 1 by Fs minus sigma M by sigma U. So how we got this equation? How we got this equation? By means of taking this Fs inside this particular thing. You can able to see this. I have taken this Fs inside. So 1 by Fs minus sigma M. Again this Fs, or it will come back to the numerator by default, and this Fs get cancelled. So sigma M by sigma U I am getting. Yeah. So finally I will be getting 1 by F, that is 1 by N factor of safety. We are denoting the small n also. So take everything to the other side. So sigma V divided by sigma V minus sigma M. So minus the other side means plus sigma M by sigma U we are getting. So it is 1 by N, which is equal to sigma M by sigma U plus sigma V by sigma E. The same method we are following even to solve for the ductile material, that is the Soderberg criteria. And in the examination point of view, this derivation is very very important. If you remember this graph, one particular graph means you can do any derivation, because what is the change we'll be doing for Soderberg criteria is nothing but we are replacing the ultimate stress with the yield stress. So we'll see in the next video where we will have discussion on the Soderberg